I'm super happy to welcome Bingsheng He, a long-term friend from Singapore today, to give our talk, our SBCLBcast talk on large-scale graph processing with all kinds of exciting acceleration opportunities. So, Nikolai will introduce the speaker, and then we'll go ahead.
Okay, thank you,
Thanks,
Torsten. Welcome, Bingsheng. So Bingsheng is a professor at the National University of Singapore, where he's also the Vice Dean of Research in the School of Computing. Before that, he was at Nanyang Technical University and MSR Asia. His work is broadly in the area of accelerating graph computations and other such computations, especially on GPUs, where he's done work for over a decade now, including one of the first systems for running MapReduce on GPUs. And he has won a number of awards. I think the most recent one among him and some colleagues, he won the Best Paper Award for IEEE TPDS for work on accelerating gradient boosted decision trees on GPUs. Without further ado, please let's enjoy this lovely talk.
And,
thanks.
And I hear you're now a distinguished scientist of the ACM. Congratulations.
Oh yes, thanks. So nice. Yeah, so we got the news today officially. Yeah,
congratulations.
Thanks. Thanks, Torsten, for inviting me for this workshop series. It's really a great thing that Torsten has set up this workshop series in this pandemic. So we have nothing to do but listen to workshop, right? That is the fun part. And thanks for Nikolai for his nice introduction. So today I will share with you about large graph processing on heterogeneous architectures. Let me move on. Okay. Let me do my screen. Okay. So this is outline of my presentation today. I will first give an introduction quickly, and then talk about graph processing and then heterogeneous architecture. And then I will pick the two of my recent projects. One is ThunderGP graph processing on FPGA, and then the other one is actually we do a more complicated graph processing, is a constraint sorted paths on GPU. And finally, I will conclude this talk and outline some future work. So graph is quite popular nowadays, no matter in database, in supercomputing, in distributed systems. I don't need to mention more on that. It's actually a lot of applications. We talk to different industry, even government agency. Actually, they have a lot of challenges come from this graph. Graph is de facto data structure for representing the relationship between different entities. So the entities can be people, can be the road network, can be whatever you can imagine. So this is really pervasive. And if you look at the graph, you can see actually it's like the graph size vary a lot. So we do see very big graph, as you can see on the right hand side. It's like you have 100 tera scale, but on the other hand, we do have some relatively small graph, it's 100 million or even smaller with in terms of number of vertices. So that's why it's quite challenging and also interesting to design some system to support this wide spectrum of graph size. And the other one, as we know, graph actually is many graphs are very sparse and irregular. So that poses a lot of challenges in system design. For example, sparsity actually pose the challenge on the graph storage, and irregularity actually pose the challenge on the memory access. Particularly, a lot of random memory access will cause the memory system like underutilization. So this is really challenge here. So if you learn about big data system 101, then actually you can see graph have all the 5V, so-called 5V challenge in big data challenges. So volume, we already mentioned that. Variety, we also mentioned this. Velocity, actually many graph can be dynamic. So actually like Facebook and also in networking, a lot of the edge or vertex and even the properties on the edge or vertex actually can be changed along the time. And the other one is the Vervexity, is about the precision of the data. So actually recently we have done some initial work on graph neural network training, we find that even we can sparsify the graph for like almost like to 10 to 20% of the original graph size, we can still do GNN, graph neural training, quite effectively. So that actually is the part that very interesting, also very challenging problems. Of course, in the end, we want to have the value of the graph processing. So let me give you one examples to go through with you. Actually, recently in Singapore, we have set up an institute named AIDF, Asian Institute for Digital Finance. So there, actually, my research is responsible for trying to research on how to detect the fraud, basically fraud in digital finance, in a real-time manner. So our technology is based on graph. So as you can see, actually graph can represent the relationship between different entity and merchants and items and even the transactions. So I give you some example here. So one example is we actually can use a path analysis to identify the like a human payment fraud. So the interesting thing is why we want to use path is that there may be some point of interest in the, for example, here we have one point of interest actually is the device actually evolved in the previous fraud cases. So this one is a point of interest. So we want to identify some path actually related to this point. Okay, so of course this transaction happen in real time. So that's why the detection of this path analysis also need to be done in real time. The other one is money laundering. So it's like many work has shown that actually there are some patterns. For example, here is a tripartite subgraph matching. You can actually based on this to identify the money laundering. And also the merchant fraud can be formed as a cycle. This actually can be found in many online businesses like Taobao, Tmall, and also like Amazon. Okay, so there are many interesting patterns we can see, but on the other hand, let's go to review a bit on the trend of heterogeneous architectures. So so we have seen people talk about the end of Moore's law. So because I think as the processor technology advance, we have witnessed the diminishing gain on the performance, and that's why we actually have a lot of designs of options on heterogeneous architectures on GPU, FPGA, and even ASIC recently. And let's look at them one by one. If you look at them, actually, this shows you the GPU. Okay, this GPU shows you, as you can see here, the bandwidth and the computation power of GPU is much higher than CPU. And more importantly, I think the growth rate is higher than the CPU also. So I think there is one saying, there's Huangs Law. Okay, this is so-called Huangs Law here. So it grows, the GPU power actually grows faster than the CPU. And this is similarly, we can see the trend of FPGA in the past decades. So you can see the capacity in terms of the number of cells in number of logic cells in FPGA also grows almost exponentially in the past decades. And this so give you another view of FPGA on how we actually increase the logic cell as the technology advances. So in terms we have finished talking about the processor side. If you look at the storage side, also something very interesting happened in the past decades. So as you can see, we show the price the storage price in terms of like USD per megabyte here. Something you need to pay attention is this is log scale. So that's why if you can see this, it's like the storage price dropped significantly in past decades, almost like exponentially decrease. So what this means is actually the storage becomes affordable in terms of memory we can done in memory computing. So why we have this in memory computing, my perspective is that, so although we say big data, right? So a lot of data has been generated, but I have seen so many applications actually, and I find that actually their working set doesn't grow exponentially. As the outside claim, we have a lot of data, but the working set itself, I mean, the frequently accessed data actually doesn't grow exponentially. So for example, the social network, we have the population. It's actually bounded by the population. the population won't grow exponential year by year. So that's how we actually have the hope that we have in-memory computing, or even more like a scale-up machine here. And this shows you the internet bandwidth. Again, is like in the past decades, like increased dramatically. And this is the data center network in terms of, you can see, we already see 100 gigabit per second bandwidth Ethernet, but we will see like a 400, even more in the future. And on the other hand, the price also dropped significantly. So overall, you can see all this comes up. We already have very powerful and more affordable hardware in the market. And even make it more interesting is that many of those heterogeneous architectures already been so-called being used in the clouds, like Amazon, Alibaba, and so on. So we can actually use them as long as we have a credit card. So this really lower the barrier of hardware accelerations. So you can imagine this is something that we are looking forward to. So on the process side, we definitely have more cores, and also we have heterogeneous architectures inside due to as we expect that we have more computation intensive workload like deep learning or whatever. And on the storage side, I think as we mentioned, the price will drop, and then we have more powerful like memory system also. For example, DCPMM, like a long volatile memory, is already on the market. 3D stack memory can offer over 400 gigabyte per second bandwidth is also available. So this really make the memory system also really powerful, and also infinite band in the network. So really we are in a great time of heterogeneous architectures. So of course, they are beyond. Torsten just mentioned that they set up one quantum computing center. So of course, this really happened. I think it will be beyond 10 years or even longer down the road. This is my own guess. Okay, of course, Torsten may have different opinion. Okay, so but anyway, we're looking at just now the heterogeneous architectures. But I think in long run, we can see more radical computer architecture will appear. For example, one thing is that specialization is that we're looking at, I think there may be more domain-specific architecture will appear, because I think, as I mentioned, because of the cloud, because of the emerging application like deep learning and also other learning applications, I think definitely we will see more domain-specific architectures. And I think the other one is the close to mass physics, is like quantum computing and also maybe other like DNA computing. A lot of interesting things happen in computer architectures. So definitely there are many opportunities for us to research on big data. So here we talk about graph processing on future architectures. So in the past decade, so actually we're looking at how we can actually architect a parallel graph processing systems on heterogeneous architectures. So we start with looking at this landscape from top down. We actually motivated by a lot of applications, as we mentioned, fraud detection, and also maybe some constraint shortest paths from the port auto vehicle, like Singapore is a port, has a big port. They're trying to deploy auto vehicle there. So real-time route planning becomes a very important task for them. So they actually model them as a graph processing problem. So anyway, so this is application. And then we actually abstract them with the building blocks, as we mentioned here, BFS, shortest path, PageRank, community detection, and so on. So these are, we expect we have some common building blocks. So why we abstract them in the common building blocks? Because we find that the graph processing are actually very heterogeneous also. I mean, one size does not fit all. So that's why we try to identify the building block. But in the end, still, many applications require many quite different building blocks. But on top of that, we devise one-time scheduling. And then after that, we do parallel graph processing here. And then this actually is a lot of research has been done. And also more research has to be done. Okay, like we need to care about the parallelism, memory consumption, energy consumption, and so on and so on. Of course, as I mentioned, FPGA, ASIC, CPU, GPU are very different, and also they need we actually need different programming models. We actually need a different optimization in terms of memory and parallelism design. So that's why we also have different program model here. Is like whether it's vertex centric, air centric, or even hybrid. Okay, so all of this actually related to parallel graph processing. And the last but not the least, I think graph is really like graph is really like has a very variety there. So that's why we have one special component is a so-called pre-processing. So the pre-processing is very important for graph processing in the sense that we need to care about how to store the graph, for example, graph layout, because as I mentioned, graph can be sparse, can be irregular. So that's why graph ordering also matters. Of course, when the graph is big, in order to fit into cache, to gain the cache locality, we also need a graph partition. So all overall, is like there are many interesting issues we can do, and there are many other research issues to be done. Okay, so in the past we have done quite some work. So this is just a quick tour of our work, but I just give you some overview here. Then I will dive deeper in some of them. So we as I mentioned, because at the day one we try to build graph system to actually support different applications. So for example, we build Medusa. Actually, is the we almost like started the project like 10 years ago. It's one of the very early graph processing system on GPU, and then we actually do a more complicated operation like a subgraph matching, as I mentioned in the fraud detection applications. And we also do some very interesting work is on more or less like domain-specific architectures, is graph accelerators. Here we here the design also, and also this is focus on general design, but we also find that it's not general system is hard to achieve the big performance. We need to care about the graph structure also. So that's why we also have another thread of research is how to make the system more aware of the graph structures. Like for example, we have Flock to try to coloring the vertex so that we can increase the concurrency. And we look at the path, the D graph, we look at the path so that we can actually analyze the dependency among the state propagation so that we actually can increase the rate of convergency. And there are C graph is handling concurrent graph queries and the graph partitioning also. And all of this actually we want to make it like more specialized to some graph structures, aware of that, so that we can optimize based on the graph structures. And then we also recently we have something very interesting is that because of also driven by the fraud detection projects, we are looking at the dynamic graph. So we actually really want to develop a very low latency and processing for streaming graph. We call streaming graph on the wire. So this is just beginning. We have done some dynamic graph research on GPU, so-called GPMA. I will give you some details later. And we have make a streaming Sounder GP is ongoing. So we have some research collaboration with Xilinx on this project. So let me go through some of them. So one graph processing system is very important. So since 2008, Google released is Prego, the system for large-scale processing. Is considered to be the math reducer for large graph processing. Since then, a lot of graph processing systems have been developed for CPU, GPU, and FPGAs. So they, of course, they have a different design purpose here, and also they may have different performance. So one thing I want to highlight here is that we actually in 10 years ago, almost like 10 years ago, we start with the project Medusa. So, and then we find that actually like the Prego Graph Lab, they adopt a very single API called compute. So on per vertex. So this kind of single vertex-centric API actually is not good for, it's not efficient for GPU with thousands of threads. So why is that? Because you can think about that. Graph is irregular. So each vertex can have very different number of neighborhoods. So it can process a lot of number of different messages, and also think about PageRank, right? So, and also many other applications, they can be, the load can be very different among the vertices. So that will cause a lot of thread divergency and a load imbalance. So our design is that instead of have a single compute API, so we actually divide them into a very fine-grained API with the Vertex API and Edge and Message. So basically, we actually decomposed one compute API into 3 API so that you can actually implement the logic inside each of the API. For example, if you do PageRank, Vertex API is actually try to apply the ranking function, and Edge API is actually to try to send the partial rank along to the neighborhood. The message here can be empty. Okay, so this just give you some idea, because we have 3 fine-grained user-defined API. So the underlying system, like a Medusa, can actually have the flexibility to schedule those workload on different threads. And in fact, that can have a more load balancing and more efficient to, for example, take advantage of the collapse success of the GPU. So actually, many later GPU systems adopt this fine-grained API design. The other one is, as I mentioned, GPMA, is that we want to support streaming graph. So graph structure is like, you think about that. So because graph is very sparse and also irregular, so by design, if for static graph, I mean, if the graph is static, then we actually design very compact data structures. Usually is the CSR or the variant of CSR. So if you think about that, it's very compact array with order. Okay, with order. Why I say with order is that because you think about CSR, you go from the vertex, and then there's some range that we present as the neighborhood, the vertex of the range in the label array, right? So this is the simple form of the CSR. So, but anyway, the idea is very compact, and also there are some order within the array. But if you think about, if the graph have some deletion and insertion on edges, then how can we support that? It's very, very difficult, right? Because the array is very compact. If you want to support the dynamic graph, the only way is that you have to rebuild the whole array upon even some minor updates, right? Or you may have the other way is that you can represent as some linked list or whatever. Okay, that is actually hurt a lot of performance in terms of the scan performance. So here our idea is that can we have a better support for the update performance, and meanwhile we can actually maintain the better the scan performance, is the query performance. Okay, so we actually learn from some well-studied structure called PMA, packed memory array, from the theoretical computer science field. So in fact, I did that when I was a PhD. I did cache or Believers query processing at that time. So I wrote a practical PMA by myself. But that's why I tell my student, can we use the PMA to support this dynamic graph? So actually it works. The idea is here. So idea looks like, instead of store into a compact array, you can see in this array we have some holes here. So the holes actually is like to allow the future insertions. Okay, so you may wonder how we allocate this. The tricky part is how to allocate these holes and how many holes we allocate on each region. So in fact, the PMA, there is a way that you can, they try to have a lower bound, upper bound, whatever. Okay, it's actually, there's a mechanism inside the PMA paper to actually, there's a way to allocate the holes so that you can achieve the optimize, the amortized insertion complexity of these, and even on average log n. So this is optimal, you know. So, and then actually based on this, we can achieve very good insertion performance. As you can see, we compare with linked list. Okay, this is the adjacency list, the green one. Okay, and then if you look at the after optimization, this one is the wet one. This is hours. Okay, the y-axis is the time. So this is the you can think about the insertion site. Okay, so the number of edge we need to insert into the CSR. So of course, the other one is as I mentioned, compact one is the CU sparse CSR. I think not surprisingly, this one is like in the purple one is CU sparse runs very slow. Okay, and then our approach is quite similar to at the adjacency list in terms of insertion performance, and of course it's much better than the CU sparse CSR. And something is not shown here is that our query performance is very similar to the CU sparse CSR, and the query performance is much better than adjacency list performance. So that achieved the goal that we have a very good insertion performance. Meanwhile, we have reasonably good query performance. Okay, so but overall, you can see, give you some flavor is that we find that in the past decade, something lesson is that one size has fits all is again and again we have this remark from this. So the algorithm matter, the architecture matter, and the design matter. And on the other hand, we also see we need a better benchmark on this. In a sense, we have seen so many papers using BFS, PageRank, and so on to as benchmark. Even for us, we're still using that. But I think it's time to change. Okay, so that's why we look at what are existing ones there. So in fact, besides the simple ones, there are a lot of interesting applications appear like GNN, as I mentioned, graph neural network, subgraph matching, constraint sorted paths, and so on and so on. This is really diversify the benchmark itself. So I think it will be very beneficial. We will build a benchmark based on them. So, and then the other one is we do see in terms of parallelism, we do see many layers of parallelism in terms of graph system. One layer is interquery. So in fact, we work with some agency, like as I mentioned, the port of Singapore. So they actually have a lot of small query in terms of the road planning. And then it's a matter that we need to also exploit the interquery parallelism rather than just exploit the intraquery parallelism right now. Right now, a lot of papers work on intraquery parallelism, how to parallelize a BFS, how to parallelize a PageRank, and so on. But I think we need to pay more attention to interquery parallelism, and we need to identify the sharing and address the intent, the contention between the queries. So in fact, we have one ongoing work and submit to Sigma. Okay, so maybe if there is another chance, I can share with you on this in our next talk. Okay, but even just in interquery parallelism, we identify as the workload change, actually the interquery parallelism also has to be revisited. So I show you one thing here is that this is the performance of the constraint sorted path on GPU. So if we vary the number of threads we need to use in constraint sorted paths, you find that actually it's very interesting is that we do see a concave. So there's some point that we have a good point. I mean, basically it's the sweet point. But sweet point is actually can be much smaller than the number of threads allowed on the GPU. So that means actually sometimes more parallelism actually leading to worse performance. So I will show you more details later on this project. Okay. So now let me dive deeper in two of our recent projects. One is Thunder GP. The other one is I mentioned is constraint sorted paths. So FPGA has been growing in a lot of scenarios. It's like in data centers, I think even in supercomputing, we are talking about how to leverage FPGA in supercomputers. And also there are many studies showing that FPGA can actually have some benefits in terms of performance in some data center applications. So why we want to do this? Actually, with the motivation, of course, as I mentioned, graph processing is quite pervasive. And on the other hand, we do think this is the lateral match, and also pros and cons here, okay? A lateral match is fine-grained parallelism. So because we think the graph, by inherently, actually the vertex and edge has a very fine-grained parallelism, right? So on the other hand, FPGA, because it's a logic cell, and it's just you can think of it's a collection of hardware resource in terms of logic cell and memory cell and interconnects. So that's why it will be ideal if we can actually map this parallelism of graph processing to the hardware parallelism of FPGA. So this is our initial hypothesis of this project. And then, of course, there's some benefit of FPGA, like a lower power consumption and so on. And even more beyond that is that we have a plan, more ambitious plan is that we want to build a domain-specific architecture on that. So we have some collaboration with the Huangs University of Science Technology in China. So we really want to tap out a chip based on the design. But this is, of course, this will be a longer term goal. But FPGA can be used as an intermediate step towards this long-term goal. So that's why we want to do that. But before that, how we use the tool, there's still one decision we need to make. In the end, we decide to use a high-level synthesis, the so-called HLS here. We want to develop the system based on C or OpenCL. Okay, why we want to do this is that because we have seen so many applications for graph processing. So there is, I mean, it's quite challenging if we want to use, for example, RTL, due to its long cycle of development. Because we have many applications, the application can change from time to time. So that's we want to have the easy of programming environment. So that's why we want to use the HLS. But the challenge of HLS is that can we deliver the performance actually similar to RTL, right? This is the, I mean, on the one hand, programmability is important, but performance, I think, is even more important, right? So that's why we want to see whether we can capture the best of both worlds. Okay, so that's why we come up with this project, Sounder GP. And let's see. Okay, we still have some time. So we adopt some a fine-grained API model. But due to time, maybe I just no need to introduce the basic here. If you are interested, you can read the model by yourself. But I want to give some high-level idea to you. Is actually in the system. One of the key bottleneck is on the data shuffling. So no matter whether you do vertex-centric, edge-centric, or hybrid or whatever, because graph is irregular, there is one stage, at least one stage, we need to have the data shuffling, and then this is more or less like random. So this really killed the performance. I will tell you why. Okay, but anyway, let me formulate this problem here. So basically, we designed the Sounder GP in terms of the hardware pipeline. We call it PE here, processing element. So the Sounder GP actually have multiple PE to process the edge here. We use edge-centric model, so the edge in parallel. But anyway, it's not needed for understanding problem. But at the end of the day, you can see here we have the stage 0 basically is the producer. We have so many tuples to be actually sent to stage 1. This is the consumer. So basically we have 8 PE as a producer and 8 PE as consumer. So the producer and consumer relationship actually defined by the data format is the destination. So destination can be your neighborhood, for example. Your neighborhood is the vertex ID of your neighbor. So this is really like a random, right? So because you think about you try to give your partial rank in page rank to your neighborhood. So this operation can be formulated here as a data shuffling. So here, I think we have, for example, this simple example shows you we have 8 tuples to be sent from stage 0 to stage 1. Okay, because we only know the DST at runtime, and also it can be different from time to time. So that's why in compiler, there's no way we can actually have static compilation on this. So we need to handle the data dependency. Meanwhile, we want to achieve the high parallelism. Okay, so we do have see the constraint of HLS. There's no fine-grained logic, and also we as I mentioned, because it's one-time dependency, there's no way that the static analysis can extract the parallelism. So we look at the existing approach, and then we see the first approach is that we can do polling. The baseline is the first baseline is called polling. So the basic idea is that for each of the consumer PE, we will try to poll the upper. We will try to poll the producer whether the tuple is available or not, and also whether the tuple is going to this PE or not. So you can see, although this approach of polling can do in parallel, but each of the PE in stage 1 need to do polling, and it has to poll 8 times of the upstream PE. So that's why ideally you will pay 8 cycles, because you need to poll 8 times here. But we want to, in fact, we want to achieve 1 cycle for 1 tuple. So this is a cycle is really a lot. And also as the number of PE increase, that will actually increase a lot also. So polling cannot work. So what about the other way is, instead of doing polling, can we do push? Actually push is we call convergency kernel. So instead of polling, why not we do push here? As you can see in this figure, we actually do from the upstream PE. Actually, each of those all those PE, we do push here to push to each of those downstream PE here. So the problem of this is, of course, you can see the runtime data dependency left to the compiler. That's good. Again, this can be done in parallel, in a sense each PE you can do. But the problem is there is a long initialization II here. So in fact, in our experiment, it's hundreds of cycles. Again, this approach cannot work. So in summary, if you see polling and convergence kernel, it can actually cause very high overhead to solve this runtime dependency. So if you hold on a minute, okay? So if we visit this problem again, then we find that the actual problem of this runtime dependency is that we don't know how many for each consumer. Okay, for each consumer, we don't know how many tuples will go to me, right? If I'm a PE, I don't know how many tuples will go to me, and also we don't know which tuple will go to me. Okay, this caused the runtime dependency. So on the other hand, if we know which tuples go to me and also how many tuples go to me, then each PE can be processed in parallel, right? So this is the basic idea of our solution. So we want to design a hardware. So basically it's here. Oh, it actually stopped my. So the basic idea is here. So we actually have a decoder for each of the consumer. So just now is a PE, then we have a copy of this decoder. So the design of this decoder is to try to tell the number of valid tuples to that PE, and also the position of the valid tuple to that PE. So if you think about that, so basically we can add flag to each tuple. Basically, is 0 is to valid to that PE. 0 is invalid to that PE. 1 is valid to that PE. So if you do this flag, we only have a limit number of possibilities from 000 A0 to 11111 A1. Okay, so basically none of them belong to me. I mean, belong to that PE, or all tuples will go to that PE, right? So you think about that, you only 256 combination. So we do a decoder. We actually build more or less like a hash table, and then we do encode is like the number and the positions. We design this into the BRAM so that it can process very fast. So since each of the PE has this decoder, then all the PE can process the shuffling in parallel. In this case, of course, the trade-off is we actually consume more BRAM to trade for the parallelism. So with this design, actually we can process one tuple in one cycle, and also we can fully utilize the memory bandwidth. So we have other optimization here also. So like caching, coalescing, prefetching, and so on, and the pipeline design and so on. So these are also very important. So so in the end, we have come up with the overall architectures. It's like we have built everything on the FPGA, on actual hardware, and then we actually have the build up. It's like we also have some automation here. So due to time constraint, I won't go into detail, but the basic idea is that we allow the user to develop to define the API on the graph accelerator like Vertex, Edge, and so on, and some host API, and then later part is the automate we generate these synthesizable accelerators. So I will skip that. So this just give you a look at our system. You can actually do it like, for example, SPMV. You can actually program it as in C. It's like very simple one, okay, rather than you use RTL. So we actually evaluate the system on Xilinx and Intel board with some wheel graph. So this performance shows you, this figure shows you about the performance of the shuffling itself. If you look at the shuffling itself, we actually compare with the polling, compare with the convergence kernel, polling, and also our paper Sounder GP. We actually have look at the speed up actually can be over 6 times to polling and 100 times over convergence kernel. And this figure shows you, shows you the individual memory optimizations. So again, you can see different memory optimization actually very important for the performance of graph processing on FPGA. But overall, in the end, collectively, when we apply all the optimizations, we can achieve a speed up of 32 times. So if we compare with some state of the art about based on RTL, so this is based on RTL. We just collect from their paper, and we find that our throughput can be like 1.4 times or even 3.1 times higher than their performance. So we have make it open source and also have been featured in Xilinx website, and we will present a tutorial in HPCA 2021. So as I mentioned, Sounder GP has done a very good job in handling the graph, but it's not really, still there's some chance we can further improve it, because many graphs can have very skewed distribution like Parallel Law. So we do have some further optimization in how we can allocate the resources in the pipeline. So this is really under submission. Okay, so we can skip that. We can skip that. This one is PageRank performance, handling the skew. Okay, so we now this is about FPGA. Now let me quickly go through another project, Wine. Okay, so as I mentioned just now, we have talked to our port authority in Singapore. So they have really like in 2025, they're trying to make the port, the cargo delivery automate within the port. So they actually pose a question to us because their existing solution cannot solve the problem. So they have the lateral in the pod is like with millions of vertices. The graph is not that big. It's not billion scale, but it's in the dozens of million scale of in the high resolution map. Okay, you can consider it's a very fine grain and high resolution road network. And at real time, they need to schedule all the cargo in the pod. So that's why the performance is very important. So in the end, we find they actually have the operation is actually do constraint shortest path. They not only just look at the shortest path, but they also pose some constraint on the shortest path. For example, they want to look at some shortest path. You must pass some checkpoint, okay, and also you must pass some like healthcare check or whatever. There's some point that you must pass, and the other one is you need to have some throughput guarantee, this kind of thing. So anyway, in the end, you can formulate as some constraint to find the shortest path. So so a standard solution is try to have this the label propagation solution. So in the label propagation solution, the process looks like this. So we actually maintain a frontier of a potential solution. We call it label. So, and then in each step, we can actually expand some of the labels, and we grow one step further. Is actually can generate some new labels. So these new solutions. So you can see this expansion actually can be done in parallel. We can decide how many labels we can expand. So in this process, you'll find that we will have a problem of exploit and explore. What does it mean? If we expand more, we can explore. Ideally, we can expand more labels at one time to take advantage more parallelism. But the problem of this is that it will also maybe generate more new labels, and later it will be pruned also. Okay, so basic here is that you can do explore to generate to search the solution faster, but on the other hand, you can also do exploit to try to prune the solution more effectively. So there is a trade-off here, as I mentioned just now. So as you have already seen the figures, and in fact, this suitable degree of parallelism is quite tricky in the sense that it can vary for different graph and for different applications and even for different constraints. So and of course we also have different hardware also. So overall, all this actually is quite complicated, but we have one very simple solution. Is we try to use the so some machine learning approach. Here is we just use a simple one, auto regression forecast model, to model the growth and the prune of the process. So actually, this is we do it where our model is quite accurate, as we see in the result. And based on that, we also have highly efficient pruning based on GPU shared memory. We propose two-level pruning. This first level is actually approximate pruning, which is fast, but not necessary to be very precise. Okay. So, and then we have tried different application on wheel graph. So this is the overall speed up. So if you compare with the baseline, the CPU baseline, so we have 18 times speed up on different queries on wheel graph. And then this is scalability graph. Result is really important, as I mentioned to you. So we have the pod authority actually have millions of vertices, and here you can see the query time is less than 1 second. I think it's in around a point something second. This is our solution. If you use a CPU, the existing solution, actually you can project up. They cannot satisfy their requirement. So that's why we actually use this solution to solve their to solve their problem in practice. So we also compare with approximate solution. The overall result is that we can achieve, because we actually solve the exact, we give the exact solution. So basically we don't have error and we don't have the index building. You can think about this in more or less like brute force calculation, but we do give a very exact solution, satisfying the port authority requirement. And meanwhile, we can actually give quite comparable response time to the approximate solution. Okay, so there are some other interesting work we are ongoing. So and then we do want to share with you again, maybe physically in 2021, or even maybe in the future. So I want to conclude this presentation here. So as I mentioned, graph processing or heterogeneous architecture is very interesting and has a lot of problem to work on, no matter volume, variety, and we actually try to explore vorexity and velocity in the coming 1 or 2 years. And we have open source some projects. If you are interested to use or interested in contribute, you're welcome. So as I mentioned, this is really challenging, but I think although graph processing has been researched for decades, but in terms of systems, in terms of graph processing on heterogeneous architectures, I think it's just the beginning. So we have seen many interesting problems and to be solved. The first one actually is very interesting based on the Sander GP. We have, even though we make significant improvement on FPGA, okay, but still we find that the current absolute performance is just similar to CPU, one socket CPU, is far below than the state-of-the-art GPU solution. So we do try to understand the problem. So we find that actually nowadays FPGA should equip with high bandwidth memory. So for example, in our CIDR 2020 paper, we do see some promising result if FPGA can be equipped with high bandwidth memory. So, but overall, in terms of graph processing, is still an open problem. So how can we actually achieve a higher performance with FPGA? So that's why we're looking at streaming graph on the wall, because I think now if you use FPGA in a similar way as a GPU, then the performance may not be as good as the solution on GPU. But we're looking at the advantage of FPGA is that they have a lot of I/O interface. Like for example, you directly can go through, can pick up the packets from Ethernet and so on. So that may be chances. And on the other hand, we also go beyond simple graph, so that we actually will, particularly in the fraud detection projects, we not just looking at the graph structure, but we also need to look at the property on the edge, on the vertex, and also the dynamics of those properties. And also we need to go beyond the graph model. As we see here, we rely on the basic building blocks, but we do hope that we will have something like SQL. So we want to have the declarative query languages like Cypher, Gremlin, but this is just a starting point. It's not ideal for many applications yet. So I think we still have a lot of interesting research can be done there. Okay. So this is the reference. Okay, thank you.
Thank you.
Yeah, thank you, Bingsheng. So before we go to questions, I do want to mention that this was the last SPCL BCast talk of 2020, and we will be picking up again in mid-January. So please check our website for details on upcoming talks.